everyone, this is Dr. Calkins. Today we're doing experiment 6. This is Twizzleranium and M&Mium. Those are just cute candy isotopes. So today we are using Twizzlers and M&Ms, so if you can find some of those, you can follow along at home here in a little bit. So after we get through the busy work, you can pause it and follow along at home if you want. Otherwise, I'll be doing it for you. Before we get to lab, we need to do a little bit of practice. As we talk about nuclear chem, we need to understand that some nuclei are unstable. And when they're unstable, typically because they have too many protons or compared to their neutrons or vice versa, they can release particles or they can release energy, sometimes both. So the things that we're going to be looking for and the things we've covered in lecture would have been alpha emission. Alpha emission is the loss of a alpha particle. That's a 4/2 helium atom. The reason that we call it helium is because it does have 2 protons. It has a mass number of 4, so it's most like helium, the abundant isotope of helium, helium-4. The issue that we have, though, is helium has no electrons. So even though we don't write it in this chapter because it's not important, it's not an actual helium atom because it doesn't actually have any electrons, because it was a former piece of a larger nucleus. Alpha is the only one that's going to change the mass number. We'll see that in a minute. So watch out for that. That's the easiest way to recognize alpha emission in your homework, is watch out for that change in mass because we are losing a mass of 4. Beta emission is the only one that moves right in the periodic table. Beta emission is basically just losing an electron, but what's unique about this electron is this electron came from the nucleus. We've never talked about electrons being in the nucleus, so that's going to be a topic for a previous video. But what's most important here is that's a negative number, so when you're losing negative numbers, you're going to be moving forward in the periodic table. Electron capture is going to take you in the opposite direction. Notice most of these say emission. And the reason they say emission is just like a car emission, they're going to be coming out of the reaction, whereas electron capture would be coming into the reaction. So a question you may have had early on is, why don't electrons that are attracted to their protons just get sucked inside? Turns out they can, and that's through electron capture. Electron capture and positron emission will be 2 ways of doing the exact same thing. This is a way to move left in the periodic table 1 box, whereas beta moves you right 1 box. Alpha is the only one that moves you back 2 boxes. Knowing that pattern is very important for your homework and to understand nuclear chemistry in general. Gamma ray emission is really no change in mass or direction. It's just pure energy. Oftentimes gamma rays are produced along with alphas. So as we practice, we need to recognize that there's a trend. This is probably the most useful chart of this chapter to recognize where atoms can go. So if you find an atom on the periodic table, know that if the result takes you forward, it has to be beta emission. If it takes you backwards to the left in the periodic table, that could be positron emission or electron capture. And if you go back 2, that's going to be alpha emission. And notice that's the only time the mass is changing ever. The rest of the time the mass stays the same or the mass stays the same. So either we're increasing our atomic number, moving to the right through beta emission, or we're moving to the left either by positron or electron capture. In all 3 of those scenarios, the mass number does not change whatsoever. So if you see that mass number change, it has to be alpha emission. So definitely take note of this chart. Very important to realize alpha emission is the only one that moves to the left twice and the only one that the mass number changes on. So we're going to do a little bit of practice. The easiest way to get good at anything is to practice. So as we practice, we're going to look at how atoms can change. We already know, regardless, just looking at the periodic table, if we're number 92 on the periodic table, if we are this new isotope of uranium called Twizzleranium, we already know the answers before we ever get started, based on what we just learned. So if we look at the periodic table and find uranium, we already know that if we move forward, it's going to be beta. If we move backwards, it's going to be positron emission or electron capture. And if we were to move backwards 2, we're going to be thorium. So we know what to predict just by directions. So even if you're not good at math, you can recognize forward from reverse or reverse 2. But remember, when you reverse 2 through alpha emission, that mass number will also change along with the atomic number. So let's try one. As we try these, remember that you do have calculators if you have trouble with positive, negative numbers. But really what we're saying here is, if you're 92, but you lose 2, what's left? Well, remember the arrow is like the equal sign. The numbers that are over here have to equal 92. The numbers that are over here have to equal 234. So 92, and we, in this case, can subtract 2, we're going to get 90. And the reason that works is because 90 plus 2 equals 92. So even though nuclear chemistry sounds pretty scary, it doesn't have to be if you just do the math. So 234 equals 4 plus something, so it's really just 234 subtract 4, and you get 230. So again, top number, mass number, bottom number, atomic number, that's the number of protons. Since this is the number of protons, that's the atomic number, we just need to look at the periodic table and find out who is 90, other than maybe your grandpa. And that's going to be thorium. So TH. Just like we predicted, it moved back 2, just like it should. As we look at beta emission, notice the math here is a little bit different because now we're dealing with a -1 number. So same applies. These are the equal sign. 234 equals something plus 0, so that's 234. But notice down here, this is also 234. Notice here, also 234. Notice here, also 234. Alpha is the only time the mass number changes. Very easy to recognize from all the others for that reason alone. So with beta emission here, we have 92 equals -1 plus the answer. So a lot of students are going to struggle with this one that don't like negative numbers. They have to think, is this 93 or is this 91? Well, if it were 91, we'd say 91 minus 1, but that's not 92. If we said 93, when you add a negative number, that's the same thing as subtraction. 93 minus 1 is 92. So we need to know who 93 is on the periodic table. And we look at 93. Just like we expected, moving forward, we see Neptunium. Let's keep going. It's great practice for pretty much every type that you're going to see in the homework. Here's the only capture. Notice everything else is an emission, so everything else has something after the arrow. This one is before the arrow because it's being captured into the nucleus instead of ejected or kind of squirted out of the nucleus. So here we have 92, subtract 1, we get 90. 91. So 92, subtract 1, 91. Have a calculator if you need it. But again, adding a negative number, same thing as subtraction. Just make sure you subtract only 1, not 2. So we need to know who 91 is on the periodic table. And just like we would expect, proactinium. We're going backwards 1, just like we went forwards 1 for beta, just like we went backwards 2 for alpha. We're going exactly where we predicted before we ever saw the math problem. So, PA, proactinium. One thing nice about electron capture and positron emission is you'll never really see them in the same matching section together because you can't tell the difference. Because the same thing over here, if you have 92 and you equal 1, just like you did up here, this was 92 subtract 1, but here it's 92 equals 1 plus something else, well, that's 91 again. So we're 91 in both situations. We said that earlier. There's 2 ways to move left in the periodic table. So proactinium again. Gamma ray emission, 0 over 0, this is the favorite of students because 92 plus 0 equals 92. Again, this is energy, not a particle, so your mass is not going to change either by atomic number or mass number. And we're still going to be Tz. If you look on the periodic table, you will notice Tz is not number 92. That's our fun way of saying Twizzleranium instead of uranium. So if you want to use Tz here, that's fine. Or if you want to use 234, 92 uranium and be accurate to the periodic table, that's fine too. So I'm going to pause for a minute, let you try this next section. But keep in mind what the major difference is between this section and the top section is now Twizzleranium is the daughter. Parents come first, that's what we saw up here. So we were using Twizzleranium as the parent in front of the arrow. Now we see Twizzleranium or uranium, doesn't really matter, as the daughter. So take a minute and try these now. Alright, hopefully you had a chance to try them. Let's walk you through them. So again, the arrow is the equal sign. So 234 plus 4 should give you 238. And then a little bit easier here, 92 plus 2 gives you 94. Look for 94 on the periodic table. 94 is plutonium, Pu. Good way to check, now that we have the parent, is go back and think, did we go backwards 2? Plutonium, backwards 2 is uranium, or in our case, Twizzleranium. Same thing. Try another one. So 234 plus 0, so we're back to that same idea of 234, 234, 234, 234. Whether you're the parent or the daughter, only alpha changes your mass number. That's the easiest way to recognize it from all the others. So here we have 92 minus 1, so that's 91. Let's find 91 on the periodic table. 91 proactinium. And as we find proactinium, again, we can double check, did we move to the right to Twizzleranium, uranium? And sure enough, we moved to the right to uranium. Twizzleranium in our case, being cute about it with our candy coming up. Electron capture, positron emission. Notice we do have the same daughters, and we should. So here we have some number, subtract 1 gets 92. So 93 subtract 1 gives you 92. Just like down here, 92 plus 1 is 93. They should come from the same parent and produce the same daughter. It's just two ways of doing the exact same thing. Let's find 93. Neptunium. Last one, but definitely the easiest one. If you're adding 0 top and bottom, you stay exactly the same. Whether you use Tz, Twizzleranium to be fun, or if you look at the periodic table and you get lost because it's not there, that's because we made it up and it's really uranium. So again, if you write 234, 92 uranium, that's fine too. So as we move to the next page, the only thing that we're doing different is now we're using a candy isotope of curium. We're going to call it M&Mium because we're going to be using M&Ms. So whether this is MM or CM, doesn't really matter. But what does matter is this page is blank. So now you get to write out the entire reaction and mimic it just like the previous page, but every time you saw Tz, 234 over 92, you're going to put 25096 in its place and do the new math associated with it. I'll let you do that, and you'll be able to check the answer keys later. So we're going to take a break, get ready for lab, and then come back in a few minutes. Alright, so real quick before we jump to lab, I forgot to mention this section. There is two types of nuclear reactions that we didn't mention. The one that's most important for our sun is the fusion reaction. Our sun likes to produce helium from hydrogen. So if you add hydrogen 2 to hydrogen 2, you get helium 4. Just like fusing two metals together through welding. This is fusing two atoms together through a process called nuclear fusion. So just add them together, both mass and atomic number, and you'll get those answers. Fission's a little bit more intricate. Fission, just like the soda that you have fizzing, those carbon dioxide molecules will leave the soda. So here we're separating these just like carbon dioxide from soda, but here we're separating, say, uranium-235 in power plants, just like the ones you see in The Simpsons, big concrete kind of tower. You're going to get a barium-141 and a krypton-92, so it's never a perfect cut, but it's basically cutting those in half. In order for this to happen, it usually needs an outside source like a neutron, and that's what makes these reactions dangerous. If one neutron comes in to split it, you get 3 out. Those split 3 more uraniums, you get now 9 out, and then you get that multiplication factor that just makes things get out of hand in, say, a nuclear bomb. So the issue here is splitting is fission, and forming together is fusion. So now let's jump to that. Alright, so on page 30 we're going to take a Twizzler and talk about half-life. Half-life is the time to reduce radioactive elements atoms by decay into half their original mass. So when we think about this, we think about this Twizzler being radioactive, Twizzleranium in our case. Every 30 seconds, we're going to cut it in half until we reach 240 seconds. So in order to do that, grab your Twizzler if you have one at home. If not, I'm going to bring it down to the chart. First thing you want to do is line it up to the actual graph itself. Once you have it lined up to the graph, you need to adjust it for the size of your graph. So notice our Twizzler is too big, so I'm going to start breaking it off into that portion that represents our paper, and then start that mark up in that top corner. So there's our 0 point for our Twizzler. And if it's radioactive, every 30 seconds it's going to be cut in half. So in 5 seconds we're going to consider that the first time. So now we're going to roll over and now cut it in half. Put it up on 30, make a new mark, follow 30 up, make a mark. And we're going to continue to do this every 30 seconds until there's no, or at least relatively no, Twizzler left. So I'm going to pause the video now, give you a chance to do that at home if you're working along, or when we come back you'll see the answer. Alright, here's the representation of what just happened. Every time we cut it in half, and notice in this first little region, most of our radiation is given off in this section because that's where most of our material was that was radioactive. After about the first or second half-life, there's not a whole lot of radioactive material left to give off radiation. So when they give you a radioactive dye for some kind of screening or test in the hospital, they're going to take advantage of those first couple half-lives because that's when that machine gets the significant amount of radiation to produce an image. After a few hours to maybe days, there's not enough radiation left really to be harmful or to be visible on those kinds of machines. So what we want to do here is just connect those dots, and this is the most realistic kind of curve for half-life. So notice it starts full, gets cut in half over and over and over and over again. Each time dividing by 2 would be the math behind what we're seeing. So let's take a minute to get ready for our next experiment. Alright, so on page 31 we're going away from our uranium-based Twizzleranium and we're going to our curium-based M&Mium. In this case we're going to use M&Ms. In this case we're going to use 28 M&Ms to be the top of our graph. After that, we're going to swirl our cup for several seconds. It doesn't have to be 10. But to make this a little bit easier, we're just going to do heads or tails. We're going to assume that as we shake and rattle these M&Ms, the M itself represents radioactivity. So if the M is up, we're going to pretend that it's radioactive. If the M is down, we're going to pretend that it is now non-radioactive because it's given off its particle or its energy or both, depending on which circumstance we're under. So here's our M&Ms. If you have some at home, this would be your chance to count out 28 and find a cup. And we're going to pause and come back when that's ready. Alright, so we have our 28 M&Ms. We're going to go ahead and give this our first data point up here at 28. It's our starting point where all are considered radioactive, even though I didn't have the time or wasn't bored enough to go ahead and flip them over first. We're going to put these into the cup. And notice as we shake them, it'll give them a chance to go upside down and around. And then as we pour them out gently, we will separate them based on who has an M up and who has an M down. So as we do that, there's a partial M, quality control, lacking for M&Ms. We're going to sequester these with M's up. Those are still radioactive. The ones that have M's down, which is in this case quite a few, those M's down, those are the ones that are non-radioactive, and those are the ones you can eat. These are still radioactive. We need to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we lost a significant number. So you find our first shake, go up to, in our case, 10. Make a mark. And now we're going to take these that have M's in them, just go back in the cup, rinse and repeat until there's no M&Ms left. And we'll come back when that is finished. Alright, so not quite as perfect as we'd like. Heads or tails should be 50-50. This wasn't quite the case. But we still can connect our dots. And it turned out for me, here in lab, kind of ran out after about 7. We still have that general curve of about half. And again, because we ran out with none left, it's not a perfect example, but it is a good way to eat candy in lab and not get in trouble for it. So let's flip over one last time, go over a few questions. And then this lab is all but done. So as we look at these questions, a lot of these are very similar to homework questions. Explain the difference between radioactive and radiation. Well, if you're a nucleus that's unstable, you're going to produce energy or particles. So if you have an unstable nucleus just means proton-neutron ratio is not good, maybe too many neutrons, maybe not enough. That's what it means to be radioactive. The type of radiation that's produced, those can be the alpha, the beta, the gamma, or even those positron kinds of particles that we can release in order to make it closer. Not everything can be non-radioactive in one step, sometimes it takes many. So put that into words for number 1. It's very similar to what happens when you irradiate food. You need a source that's radioactive. You allow the radiation to hit the food to sterilize it, a way of cleaning our food without using soap. As we look at number 2, we want to know who transforms a proton into a neutron. So if you have a proton going into a neutron, which direction would we be going? Are we moving right, or are we moving left? Well, if a proton goes into a neutron, that means we lose an atomic number. So think about the ones, in this case, 2 of them. They're going to take you left in the periodic table. And number 3, they say who forms a neutron into a proton. So if we're forming a neutron into a proton, now we're gaining an atomic number. That should move us to the right. There's only one that can do that. In both cases, the mass will stay the same. And number 4, we want to calculate the half-life of our Twizzleranium, assuming we start with 100 grams. So if we start with 100 grams, we need to take 100 grams and cut it in half. But that's only 1 half-life, and that will give us 50 grams. If we're saying that the half-life was 30 seconds that we did earlier in lab, what's going to happen after 3 minutes? Well, in order to understand that, we need to know how many 30-second intervals are in 3 minutes. if you said 6, you're right. So we divided by 1. We divided by 2 once, and that gave us 50. So we need to divide by 2 again. That gives us 25 grams. Divide by 2 again. We get 12.5 grams. Divided by 2 again. We get 6.25 grams. Divide by 2 again. Running out of space, let's start going up. We're going to get 3.125 grams. Divide by 2 again. Calculator probably required here. 1.56 roughly grams remain. So notice 1 half-life, 2, 3, 4, 5, and 6. That's really the same thing as saying what would 100 divided by 2 to the 6th power be? But if that hurts your brain, just divide by 6, at least 6 times, and that's close enough. Lastly, to answer the question for M&Mium's half-life, how many shakes did it require to get our M&Ms to about half? We started with 28. Turns out our first shake was enough to get us down to 10. That was kind of past our 14 mark. So definitely about 1 shake, maybe slightly less, was enough for that one. So we'll see you next time.